Welcome back, everyone. I know I dragged a lot of you back in because it's my talk. I want you guys to listen, enjoy. So a brief overview of what I'm going to be talking about. My talk's on alignment engineering, and that's my LinkedIn. If anyone wants to connect, please feel free to scan it. So we'll structure this talk this way. I'll start by giving an introduction of how to pre-train a foundation model. And then we'll go into what is alignment, how to align the model. And we'll look at different techniques that we can use for alignment. And then I'll talk a bit about curriculum learning and how it all fits in the alignment engineering paradigm. So it all started with transformers. So transformers it was a pivotal shift that led into the modern foundation models. So before transformers, RNNs was used for similar tasks of sequence prediction, but it had some issues. Like it wasn't very easy to parallel process using an RNN, and long-range dependencies used to get lost. And so with the introduction of transformers, it has a encoding and decoding structure, which allowed it to, and self-attention. I'll go into each of the steps in the following slides. So this architecture led to higher scalability, and we could do a lot more layers now because we could parallel process. And pre-trained transformers, we could fine-tune the pre-trained transformers more efficiently too. So this kind of kick-started the whole reason for this bootcamp. So there are three types of transformers typically. There is a encoder-only transformer, or decoder-only, or the whole encoder-decoder structure. So in these transformers, the encoder typically can take the inputs and it encodes it to form the it encodes it to extract the information, which is typically used for tasks like sentence classification, named entity recognition, whereas decoder helps in generating the outputs. So it's used typically for text generation or causal language modeling. And ChatGPT is a good example of the decoder-only model. And when we use encoder and decoder together, it is useful for tasks like language translation or summarization, stuff like that. So because most of this FMware stuff was kick-started by ChatGPT or GPT itself, we will look at how a decoder-only model is typically trained, and then we'll see how the whole pre-training process happens. So these are some of the stages of the transformer. And the input, the training paradigm that's used is called self-supervision, where we don't need any labeled data, and that's why we are able to crawl lots of raw internet data and just ask the model to automatically identify what targets that it has to train itself on. So the task here is to predict the next token. So for example, if the input sequence is AIware Leadership Bootcamp it should be able to predict AIware Leadership Bootcamp is awesome. I know I'm biased, but yeah. So the process starts by tokenization. And I'll briefly mention the byte pair encoding tokenization that GPT uses. So it starts by splitting each of the character in the sentence into individual characters. And then there are multiple iterations through which it identifies the most frequently occurring pairs, and those form the final tokens. So once we have these tokens are indexed using a learned, are first indexed, and then they're embedded using a learned embedding matrix. So this GPT uses a 768 dimensional vector, and there are other earlier transformers that use 256, 512. So this determines how each token is represented in is embedded, and this is used downstream. So the reason for embedding is this contains, this kind of embeds the semantic information of each of the word in higher dimension. But this embedding does not have any positional information associated with it. And because transformers can be also parallelly processed, if we just don't give the positional information in parallel processing, the position information might be lost. So we also do something called a positional encoding, where each position, similar to the output embedding, we have a positional embedding matrix, and we kind of add the positional information, and we finally combine the word embedding that we created first and the positional embedding. And fourth, and this is the secret sauce, attention is all you need, is the paper that introduced this. And so how does attention work? For each token, so for example, in AIware Leadership Bootcamp, each of the token is transformed into query, key, and value vectors. And they all have a learned weight matrix. And to calculate the attention score for each word's query vector, you multiply it, dot product it with all the other key values of all the other words that is present there. And then these scores are together softmaxed to get the attention value. And finally, weighted sum of the tokens interaction with all the other tokens is noted. So for AWESOME, this incorporates the context from all the AIware Leadership Bootcamp is. And then what really makes transformers able to learn a lot of information is the multi-head attention. So when we do the self-attention in the previous step, it captures, let's say, the semantics or the grammar information. But there is so much more that goes on with a sentence, right? Like there is syntactic information, there is semantic, there is relevance. So to capture multiple contexts, multi-head attention calculates the self-attention several times over. And they're all finally combined together so that a very rich representation of each of the word is available. And once this multi-head attention scores are available, we add the original input along with the attention output, and then we normalize it using a softmax so that it is consistent. And this can be now fed to the next layer. And the next layer is a traditional feed-forward layer with two linear layers where ReLU activation is used. And each layer is independently processed, and once again it's normalized. And finally, all of these values are projected onto a linear layer, and the outputs are then, this is the layer that helps us predict the probability of each of the word. And finally, the softmax layers normalizes the probability. So the model selects the word with the highest probability as the next token. So a slight aside. So during training, there is no sampling that happens. So the final probability vector is what is used to calculate the loss. And finally, we compare the probabilities that we generated for all of the vocabulary against the ground truth probability. And we calculate a loss. And we backpropagate this loss to each of the layer, and we update the weights. So that is a very quick introduction to how a transformer is trained. And the early GPT was a transformer that was trained in a similar fashion for several tasks. So, but wait, I spoke a lot about how the weights are updated and everything, but what about the data? And as much as transformer is responsible for this burgeoning FMware area. Data is also key. So typically, large volumes of data are scraped from the internet or collected, and then it goes through several layers of filtering, like it's filtered for the right mix of languages. Lots of heuristic-based filterings are typically applied, and data quality measures like what is the information density of the data, and if it's just all the stop word removal, and making sure right mix of domains are being present, and data deduplication, and removing all or most toxic content. We do all of this, and so that also shows the targets on the right top of the slide. We show the different targets that we optimize for when we collect pre-training data. And finally, we have an FM when we train. So recall all the transformer training that we went through and combine it with all the large amounts of data, and we have a FM. So there is a lot of when I say large amounts of data, it's so much data usually. Like the recent openly available pre-training data corpus was about 45 terabytes, the Wine dataset, I think. And this slide kind of shows the different combinations of data used in different pre-trained FM models. And as you can see, most of it comes from web pages, except for alpha code, which is a code model. So all of the code is just code. So that was an introduction into the pre-training process, but this session is about alignment engineering. So we'll spend more time on the alignment techniques. So why can't we just use the pre-training model? Because pre-training models are typically pre-trained models are typically good at predicting the next token, or just or for whatever simple task it was trained for. Like if you take GPT as an example, it was trained to predict the next token. So just by predicting next token, we can't really go very far. So we need to adapt the behavior of the FM for our specific task for us to be able to get any mileage out of the model. So question, is ChatGPT a foundation model? Yeah, that is the right answer. So it's working. We are in day 2. Nobody said it is a foundation model, so it's awesome. So ChatGPT base foundation model was GPT-3, GPT 3.5. I didn't get the 3.5 icon. So, and it's the GPT 3.5 was pre-trained on a large corpus of data, and then we do alignment engineering where we do some supervised fine tuning and some preference tuning, and we end up with ChatGPT. So this is something I found online, and it was one of the best representations that I found of alignment. So if we just take the unsupervised learning, there's a lot of toxicity, there's a lot of bias, there's not a lot of useful prediction that comes out of it. And when we put it through different layers of alignment engineering, we end up with a nice model that we are very happy about, typically. So these are the ingredients that is required for alignment engineering. First, we need a pre-trained foundation model, and then the data that is specific to the domain. Like it could be a classification data, or it could be instructions or chat responses or preference data, like the data that says these are some of the responses that we like, these are some of the responses that we don't like. And then we can have all this data, and then we need a method to teach the pre-trained foundation model to learn about this data. So we will go into what are the different types of methods, different types of alignment methods that are out there. So as we saw in the previous slide, we need data, which means that we need methods to curate the data in the right way, or collect the data, generate the data, and curate the data. And then we need techniques to teach the model. So data alignment is a group of methods that allows us to collect the right kind of information for the task that we have at hand. And model alignment is a set of techniques that helps us teach the model about the data that we have for a specific purpose. An alignment evaluation is methods through which we evaluate how good has our model learned, or how good our model is aligned now. So for people who attended day one, they would probably recall this slide Ahmed showed. So in this foundation model era, to teach a model, we are not, or to encode a new behavior to the model, or we are not writing any code. We have to, so for instance, to make GPT 3.5 start answering to chat, we didn't have to write more code. We had to show it a lot of prompts and a lot of ideal responses, and then it kind of learned. So that is the idea. Now we have no code, and which means that the kind of data that we show forms the operational logic of what behaviors we want the foundation model to encode. So data becomes the new code, and we have to structure it. We have to collect the right information so the right logic can be taught to the pre-trained model. But getting this data is not cheap. It's very pricey usually. And though we are a bit spoiled as computer scientists and software engineers, because most of our task is available online. If we were in, let's say, manufacturing industry, talking about material defects, and our model needs to do well on material defects and needs to answer questions on that, there's not a lot of data in internet available about that, and there's no readily available data sources. In such a case, if we were to get that data from domain experts, it would cost a fortune, and there are many domains like that. So we should look into methods that kind of make the tagging cheaper, and how to make alignment methods that require less data. But that's a side quest. I really like the slide that Kehelia had. But so the three key ways in which that we collect data right now, or conduct data alignment, is by either collecting the data manually, or having automated data generation methods. So first, one of the nicer manual data collection approaches was done by Scale and Scale AI. And Scale AI used for GPT-2 and 3, Scale AI collected the data that they used to conduct RLHF on the model. So what they did was, to ensure high quality, they first collected a few benchmark data points, and they evaluated a bunch of labelers, and they assigned a few labelers as the benchmark labelers, and they constantly evaluated the benchmark labelers' performance against the benchmark task to keep this set of let's say golden reviewers who create golden labels, and every other person's label was compared against them, so that the quality could remain consistent even through the manual labeling process. But this kind of manual labeling is very costly, and it doesn't scale unless you have lots of money and are okay with outsourcing a lot of labeling, which I recently read was not always conducted very ethically. This is not an approach that's going to scale. And other approach, which is also a manual data generation approach, but it's kind of semi-automatic, is the snorkels approach, where they invite domain experts to write heuristics and then use the heuristics to label data. So they call it programmatic data labeling. And recently, with the introduction of foundation models, they use something called a warm start, where they kickstart the labeling with a existing with a foundation model through a prompt, and then they also combine the labeling with domain expert driven labeling rules, and they get an initial set of label, and they train a model through weak supervision to label the data again, and they iteratively they analyze the data, they show all the data back to the users, and if the users find some of the data points not properly labeled, they fix it, and they use it iteratively to improve their model, so that finally you end up with good data. But this also, once again, requires subject matter experts to write the initial rules and also review the data labels, which is often costly, which is even more costly than just hiring a lot of people to label. So some of the automatic data generation methods, most of the automatic or synthetic data generation methods right now use a foundation model in some capacity to synthetically generate data with different kinds of quality filters. And self-instruct is one of the, let's say, early but foundational works in this area. So what they did was they manually collected 175 different seed tasks with one instruction per task, and they put it in a pool and asked the LLM to generate instruction based on this. And then there is another, the LLM again identifies if the sentence is a classification task or it's just like an instruction, like summarize the data or summarize. Let's just stick with summarize. I can't think of another word. And then the generated responses are filtered using a quality criteria like rogue filter. So they used the ROUG metric, and the data points that had ROUG metric greater than 0.7, they added it into the pool, and they iteratively do it until enough data is collected. So the data generated by self-instruct was used to train the alpaca models, and it ended up having reasonable performance back then. But the key problem with synthetic data generation is it's extremely hard to ensure diversity of data that we generate, because at the end of the day, we are constrained by the model that's generating the data. And it is expensive, as many people spoke about yesterday. Inference, so if you want really high quality data, at many times you have to rely on large foundation models. Large foundation models are costly to host if you want to host it by yourself, or they cost money per inference, which is both unfeasible at many points. And I also was recently reading about a paper which said that the total cost of ownership of even hosting a small model at times is significantly higher than, let's say, just paying for GPT. And they don't even have to host like really large foundation models, like even something in the scale of 7 billion to 70 billion, it's still the total cost of ownership sometimes ends up being high. So just because a model is open source doesn't mean it's necessarily free to run it. And so we saw how to manually generate this data, or how to automatically generate this data. But once we do generate this data, there are several things that we have to really worry about, like quality, how to reduce the bias, how to make sure this is the right data for the right task. And depending on the task that we are going to use this data for, which is the data alignment the data alignment target. So if it's an instruction tuning data, there are different criteria that you want to probably optimize for. If it's alignment data or preference tuning, there are different criteria that you want to optimize for. And I will talk about the different types of data in foundation model pipeline tomorrow in my talk. So I won't go too much into this, but I will talk about this more tomorrow. And now we saw what is the kind of code that we need, code or data that we need to encode, teach the model the right kind of information that we want to teach so that it performs well for the task that we are trying to align it for. Now we'll go into the techniques that we use to teach the model, which is the model alignment techniques. One of the first technique is fine tuning. I'm sure every one of you have heard of fine tuning. Yeah. So there are many different types of fine tuning methods. I'll start with the most boring one, the unsupervised fine tuning. Funny enough, there are only 2 papers I could find around unsupervised fine tuning, and but it is pretty common. I just couldn't find it in the context of large language models. But the unsupervised fine tuning is similar to traditional unsupervised learning, where there is just no labeled data. You just fine tune it on data that you think is more specific for your task. Typically, it uses a contrastive loss function to minimize the loss with the task-specific data that is provided. And for success of unsupervised fine-tuning, typically larger amounts of task-specific data is needed, and it's computationally expensive. However, computationally not very expensive. I have it wrong there, but the results may not be very good. So supervised fine-tuning. So this is the poster child that once again kickstarted ChatGPT and everything. So interestingly, the first instruction tuning of ChatGPT used a full traditional fine-tuning where all the parameters were updated, and it involves simply training the whole model weights. You just need the infrastructure, the money, and the time. But this is very resource intensive. For example, GPT-3 needs to update about 175,000 million parameters, which is crazy. It requires like 80 or 90 H100 GPUs. So another technique, which is a feature-based supervised fine-tuning technique, is from the older days of neuralware, where you freeze a lot of layers and you freeze the whole model, just add one layer on bottom and train the model. But all of these are once again very costly. So that's why people have been investigating, and the whole parameter efficient fine tuning has become really popular. In traditional supervised fine tuning, as I was saying, to fine tune Bloom 176 billion model, which is very similar to GPT, you require 3 terabytes of GPU memory, which is 70 to 80 gigabytes A100 GPU. I don't think most of the world has access to that kind of hardware. I know I don't. So that's where PEFT comes in, which is parameter efficient fine-tuning methods. They usually find intelligent ways to train only a subset of the parameters so that similar performance as if updating all of the parameters in a pre-trained model can be obtained. So for example, LoRA PEFT method only has to train about 37 million parameters of a 175 billion parameter model, and that's significant. So most of the PEFT methods can be classified into 3 large categories. There is There are some overlapping categories that I'll introduce later, but they can largely be classified as additive methods, where you typically end up adding a layer and just tuning that layer or updating the weights of that layer, or specification methods where we train only a part of the existing parameter space, or reparametrization, where they're decomposed into lower dimensions, and the lower dimension is trained and reprojected. And these are some of the other subcategories where adapters and soft prompts, which kind of cross over. So no, adapters and soft prompts are other subcategories of additive methods. So I'll try to go over an example in each of these methods. Hopefully that gives an idea for each category. So adapters. What adapters do is they usually freeze the whole model, and they end up adding few tunable adapter layers in between the existing parameter weights, and they only tune these. They only fine-tune these adapters for that specific task. Nice thing about this nice thing is we now only have to tune the adapters that we have added, and not trivially, it involves a lot of effort, but these adapters are transferable too, which has actually led to creation of things like AdapterHub, where people have tuned adapters for specific tasks for a given architecture, and they've shared those adapters. So if you're using a similar architecture, you can take the adapter and plug it in, which now introduces a new kind of asset that we can research about, play with, and explore, and promotes reuse. And the next method, which is also an additive method, is soft prompts. So what soft prompts? Interesting backstory. So there is a paper called prefix tuning, and there's a paper called prompt tuning. Both are very similar methods, and they were both out around the same time. So I'm trying to cover both of it here. So prompt tuning, prompt tuning has a fixed set of tokens that it prepends to the existing prompt, and those tokens are optimized. Whereas in prefix tunings, we add some trainable tokens to each layer of the to each layer. A few parameters are added, and these are trained for each prompt. So both of these are still additive methods, and in one of which we end up and they help encode a lot of context information. The best use case for many of this prefix tuning or prompt tuning is where instead of giving 100 or 200 examples in the context, we can tune these prefixes and add them, which helps us use the context window of the prompt for more instructions and specifying other data. And then another parameter efficient fine-tuning method is selective method, where, as I was telling earlier, we only update a specific subset of the model weights. So BiFit is one of a parameter efficient fine-tuning approach, where only the bias terms. So all of these neural networks have a weight and bias value associated with it, right? And all the weights are frozen, and only the bias terms are updated. So all of the selective methods usually have a strategy that selects, which intelligently selects some parameters to update while not updating most of it. And this particular method only has to update about 0.04% of the whole parameter space. But far as I know, selective methods haven't been very effective for fine-tuning. So, and reparametrization, and the final category of method is reparametrization. And LoRA, which is low rank adaptation, is one of the most famous reparametrization methods, and it's being very widely used. Now there is also a new method called DORA, which is an improvement on LoRA. But so LoRa's idea is so all of these pre-trained weights, if we consider it as a matrix, it is a matrix, and we decompose it into two low-rank matrices, and we only train or fine-tune these low-rank matrices. And once the fine-tuning is done, we just reproject these low-rank matrices back onto the original weights. The nice thing about this is these low-rank weights are once again reusable. So for the same model, we can have a LoRa weights of, let's say, sentiment classification task, and then LoRa weights for code generation task, and then we could have them all stored, and depending on the task that we have, we can load the given LoRa weights. And this way, we don't have to bring a model down and rehost the model again, which has its own costs, which Boyuan and Hoshang will talk about on the last day. And and there is no inference latency associated with it. And so these are techniques that are usually so the fine-tuning techniques are usually used to teach a model a new task, whereas the online or offline alignment methods are usually to teach a model to behave almost. So one of the things, so what it encompasses usually is something called preference tuning, and reinforcement learning with human feedback was once again the method that kick-started this FMware space. And GPT-3 was instruction tuned with full supervised fine-tuning, and then preference tuned with reinforcement learning with human feedback. And it's typically very expensive in practice to conduct, but it works. So let's go through each step in detail, because I think it's worthwhile knowing more about this. So first, we take the pre-trained model, and then we supervise fine-tune it on different tasks, and we have the instruction-tuned model. So here, the data on which it's supervised fine-tune is probably instruction-following data, and the outcome is that we now have a model that can respond in the way that we want it to respond. However, it can still have bad responses or toxic responses. For example, if someone asks the model what is the way to get to downtown, it can nicely say, oh, this is the right way to go about it, or like, are you dumb? Just take a left. That also is technically giving directions, but it's not the way we want the model to behave. So the next step is where we ask, we had the supervised fine-tuned model from last step. We take the model and we ask it to generate responses for a few prompts, and few responses for each of the prompt. And then we ask human labelers to rank the responses as which response they prefer, what is the order of ranking, and then we use this data to train a reward model so that we don't always have to ask a human. So this reward model kind of tries to learn how the humans are ranking the different responses, so that the reward model has an idea of what is a good response and what is a bad response. And the outcome is now we have a reward model that can generalize human preferences. And then once we have this reward model, what we now do is we have the supervised fine-tuned model that we had, and then we have this reward model, and for every response it generates, we calculate the reward for it, and depending on the reward, we use an algorithm like a reinforcement learning to teach the model through a technique like proximal policy optimization to adjust the model's parameter weights so that the reward can be, it can get more reward every time. So it's optimized to get maximum reward. And finally, so if we get more, if we are able to maximize the reward, which means that we are mimicking the human preferences from the reward model that we built in the last step. So finally, we have a model that most likely whenever you ask for direction always talks to you nicely. And but as I said, this step has a lot of human labeling involved, and we typically don't want that for scalability purposes, right? So some of the offline methods, one second, sorry, okay. Some of the offline methods that can work in lieu is something called direct preference optimization. Here, to align, like we use the reward model's preferences directly here without having even a policy update, where we first collect the human evaluators. Human evaluators here rank multiple responses, and then we train a reward model, and then we use this reward model directly to do to fine-tune the DPU fine-tunes the main model by adjusting the outputs based on the reward model's preference scores directly. So this makes the whole thing more efficient, because we don't have a costly policy update anymore. We're directly using the reward model to compute our losses. And finally, to evaluate if we did a good job aligning it to human preferences, we typically use benchmarks, which is what most of the papers at least are doing, which is quite problematic, because benchmarks are more often than not representative of, they're not very representative of real world tasks. And as I was talking to Prem yesterday, the SWE bench, which is very widely used to evaluate a lot of software engineering foundation models, are not super representative of any of the real world tasks, or how programmers actually write code, or how real world code looks like. So another way in which we can evaluate if the models are aligned well are to use human judges. Human judges are once again costly, and there's a lot of bias there, and as we know, not all humans are always created equal. And I don't mean this in a bad way, just different people have different capabilities. So I might be really good at code, and someone might be really good at evaluating the grammar. So which means that for a given task, if both of us are labeling it, for coding task, my labels might be better almost always, and their labels might be almost always better when it's about evaluating the quality of response or something like that. So people now use similar to chess games, where if you beat a similarly ranked opponent, it only puts you slightly higher up in the ratings, whereas actually tennis also uses this. And if you beat someone who is pretty well ranked, then you end up scoring a lot more, which is called ELO ratings. So people use ELO ratings to rank the human judges, and then they can pick and choose which kind of judge with a rating that they want to label the task to evaluate the FMs or FM's alignment quality. But once again, even with all these rankings, it can be very subjective. So, and it's not scalable, once again. Another method to do FM evaluation or evaluation of the alignment quality is to use AI as judge. I think Justina will be talking a lot more about it later, but I'll just quickly mention the idea is to use different FMs to judge if or a stronger FM to judge if my aligned FM is aligned well for the task at hand. But this can be very costly because recent AI as judge methods use many models with many inferences, which once again with the inference cost, if it's a cloud hosted model or if it's a locally hosted model, the infrastructure to host all the model is very expensive. And there was a recent paper by people who built Copilot. They were saying at some point they had to stop testing all of this because testing was becoming too expensive every time to run all the inferences. So if you use AI judges to evaluate everything, then for each to evaluate one response, we have to have 5 inference queries from 5 different AI judges, which just compounds the cost. And over and above, any of these foundation models can only evaluate based on the domain that they were trained on, and the shortcomings they have is going to be reflected in the judgments that they make. So not all alignment tasks can be evaluated automatically by AI judges, because let's say, once again, going back to the earlier example where if we are talking about some industry specific stuff for which a lot of web data is not available, which means that these foundation models might not know anything about something like about material design, because there's not a lot of data around it available in the internet. So once again, these are all the different alignment evaluation methods, and now we already saw about what are the ingredients that we needed, and we spoke a bit about how to collect the data to conduct alignment, and what are the different types of data that we can collect, and what are the methods to align the model so that the pre-trained foundation model can be adapted to downstream use. However, is getting all this data even in a curated way and just throwing it at the model the best way to really teach a model to do the task. Like when we teach a class or students, or even this slide, I put a lot of thought and effort into how to structure this whole thing and introduce them sequentially, right? Like, but this is the information, and if I just have the slides in a random order, it wouldn't make any sense for most of us, right? And why would, and we think similar idea transfers, where if we have all the data, or if we manage to have all the right kind of data, and we have the best way to teach the model, then we have to also organize and show the data in a right way to the model, and we have to create a curriculum and a structure to enable that learning. So now I'll talk a bit more about this whole idea of curriculum learning. So what is curriculum learning? There was a paper. I will talk about the paper a little bit first, and then I'll explain what is curriculum learning. Where what they did was, you know how they give examples in in-context learning when they prompt. They just ordered those examples from easy to hard examples, and they could immediately observe a performance improvement. And before foundation models in traditional machine learning, they were also observing if they were, during the training batches, if they were showing the easy batches, data points that are relatively easy first, and then show the data points that are harder later, they were able to see the model converge faster and performance improve. And so the idea of curriculum learning is to have some sort of a progressively complex order with the data that you have, and expose the model, expose the complexity of the data to your model in a progressive fashion. Similar to how we learn, where we first learn the basics and then we solve advanced problems. Learning the basic patterns first improves the learning efficiency and robustness. So there are two things that we can do here, right, to enable that. First, we can systematically curate the data, which is typically the longer part. Like imagine when we are designing a course, it takes a lot of time and effort to design the course in the right way, design the structure, and decide what kind of data goes where. So creating this curriculum, the first part is once we have all the data from the data alignment process, we create a curriculum, and then we incrementally expose the model to the data based on our curriculum. So this curriculum was once again like data, which I was saying data is the new code, and we have to treat data and data points as such so that we can encode operational logic with data. Now, to structure this operational logic, we are using this curriculum, which is also a new asset. And as Ahmed was introducing yesterday, I think this is a new asset that we should, and an abstraction level on top of data that we should be dealing with. And we need better curriculums to move towards the software engineering 3.0 vision. And for the incrementally exposing the data to the model, it's just how we do the algorithm part of it. Let's leave it to the AI guys for now, and maybe we can come to it later. But I think here is a bigger problem, because most of the research and at least as far as I know in practice, while there's a lot of care and effort that is being put into the kind of data that we collect, there is not really always care that's put into structuring the data or ensuring the diversity is there, or if the data is collected according to any curriculum, or if it's being exposed to the model using a curriculum. One of the first efforts that did it in the context of large foundation model was the phi models. And though they don't explicitly say it's curriculum learning, they built a data curriculum to pre-train their model. So what they did was, it's actually kind of very neat. What they did was they took the stack dataset, and then they also took data from Stack Overflow, and they took about 100,000 samples, annotated it with GPT-4. They explicitly say in the paper that they just used GPT-4 in lieu of humans because it's tedious to annotate data. And they used these labeled samples to train a random forest classifier. And now this random forest classifier's task was to see if the data is a good educational example. And using this, they classified the rest of the stack and the Stack Overflow dataset, and they created the filtered code language dataset. And then, inspired by another idea, where if you inject random, so to ensure information diversity and the data diversity when you're synthetically generating data, they found that it's good if random words from a vocabulary is selected and provided in the prompt, and the prompt was forced to include that word in a semantically consistent way somehow. And so inspired by this idea, the people who built the Phi models, they did the same to generate a textbook quality dataset for programming, and they added those datas, and then they added the data, and then they also had synthetic exercise, programming exercises data that they created, and the task that they used was docstring completion. But both the synthetic textbook dataset and the synthetic exercise dataset is only a small part of it. The major part of the dataset was the filtered code language dataset, and they used these three data to train the Phi models. What's very neat about the Phi models is it's a small model. It's like 7B. It's even smaller than 7B, and they showed that with such high quality data curation and creation, what they're essentially doing is they're doing a curriculum. They're structuring the data in a very rigorous way, and they're creating textbooks and exercises, which is curriculum. And they're using this data to train the model. And they found that with this kind of data, even a small model can perform as well as many large models at that time. And this is the process that they outlined for the first version of Phi model. And now I think Phi is at Phi 3.5, and they have models that are like 3B that can perform as well as many 13B models. While Phi approach is great, and they are very rigorous, what we need to do is make this process of creating the curriculum a lot more rigorous, so that curriculum can now become an asset, and it can be collaboratively edited. So if your team is building or fine-tuning the model for a particular task, you deal with it in terms of to do the data alignment. You deal with it in terms of curriculum and make sure that there should be some skills. Some foundational knowledge should be represented, some skills should be represented, and some compositional skills. So what is foundational skills? For instance, if let's say we want to fine-tune our model to generate code. In such a case, first we need to show the model all the details of what is programming, how to program. And like this applies even for the pre-training context, right? Like when we want to build a task-specific model, we have to introduce all the knowledge. We have to at least make sure all the knowledge that is relevant for the task is there. And then what are some of the foundational skills, like how to write for loops, how to write if statements, how to write switch cases. These are all foundational skills. And then some compositional skills, like how to write efficient code, how to test the code, how to make sure spaghetti statements are not included. So different different compositional skills being represented. And once we start dealing with this abstraction, we might be able to do data alignment a lot better and not collect all the data, fine-tune the model, and then find out that, well, it didn't work. So because all of this process that I spoke about earlier, both fine-tuning and collecting data, expensive, right? So, and for all of this, we need a lot of new software engineering technologies too. Like we need curriculum co-creation methods. We need to start versioning these curriculums. We need processes we know how to probably review code, but now what does reviewing a curriculum mean? And what is quality assurance for curriculums? Yeah. And another thing that I want to mention before I move on is these curriculums are going to be super effective in an agentic world where different agents need to be very task specific. And for those particular tasks, if you want to fine tune an agent, then having a curriculum enables us to automatically generate the data and just figure out the curriculum, and then rest of the process can be automated. Otherwise, for a task, we have to generate the data, fine tune the agent, and then hopefully pray that the agent works as we want. So this is a proposal almost, and Ahmed already showed it, but some people did not attend yesterday, so I'm just going to quickly go over it. So let's say we have all the raw data, the human annotated data, synthetic data, different types of data that we can collect during data alignment or even during data pre-processing stages. Then there should be stages where there are already stages where we filter this data for quality and difficulty, we remove redundancy and things like that, and we add it into a pool. And now, with this data, we should be starting to first create curriculum and then curate the data based on curriculum and perform data and have techniques to perform data performance engineering, which kind of helps us feed our agents. So this curriculum can be created by us or in collaboration with FMs and other agents too. That way, the abstraction level at which we are dealing with for the whole data generation process is at a curriculum level rather than at the individual data level. And once again, data used as is very inefficient, and we need techniques like data programming and curriculum programming to enable this. And I actually have an example. So when I mean by curriculum programming, I have an example for how it might look for code documentation. So let's say a code documentation curriculum is being created by in AI agents and humans and foundation models together. And some of the foundation models might be, what are the documentation standards? What are the common pitfalls when we are creating documents? Like when we put these in curriculum, we then have representative data points when we are fine-tuning the model or the agent. So we have some documentation standards, pitfalls, code design principles, and in the action-based skills, foundational action-based skills, we have the technical writing skills, the code analysis skills, and how to extract information from different tools. And in compositional skills, we have data that represents how to integrate code and documentation, adapting different types of documentation for different audience. So a loop might look like we have all the raw data. We first remove all the bad and redundant documentation examples. We add it to the pool, and then we create the curriculum that we saw in the previous slide. And this curriculum can then be iterated, modified by the whole team. And then this now once we agree upon the curriculum itself, then we can use synthetic data generators like self-instruct to generate data and serve it in an optimal way to fine-tune the model. So there's another almost open source tool now, but they also have a paper called Instruct Lab by IBM, and it's actually becoming very popular too. they use similar. They use a similar idea, where they ask. They have some foundational skills. They have some knowledge snippets, and they ask. They have compositional skills. And they use this to synthetically generate data in their synthetic data generator component. And then they use the synthetically generated data, they send it to review. And if the review goes okay, and if user is happy with the synthetically generated data, then they use it to fine tune their model. And the nicest thing that they did was, now for each task, all it takes is for someone to provide 5 question and answer pairs that represents the compositional skills, foundational skills, and 5 snippets of knowledge. And now it can synthetically generate data based on this curriculum, and that can be used for fine tuning. While they have some shortcomings, it's a very, very good starting point. And they use it's an open source project, and anyone can contribute skills and knowledge for any task. And so once you add it, you can start generating data synthetically. So to summarize, I first spoke about some of the how to pre-train a model, how to pre-train a transformer, and then I spoke about why just having pre-trained models is not sufficient. We need to align these models for real-world use cases. And then I went over the taxonomy of alignment engineering. And we also saw different types of fine-tuning methods. And finally, I spoke about the need for curriculum programming in alignment engineering. Thank you. That's once again my LinkedIn.
Thank you, Gopi, for a nice talk. We're open for questions.
Oh, thanks, Gopi. It was a very nice talk.
Thank you.
So I had a question about the AI judge, as you mentioned, in the process of fine-tuning.
Okay.
What do you think of replacing one big AI judge with multiple smaller FM models and ensembling them based on and seeing what they agree on?
I think it's a great idea. And it's smaller models still mean...
Like instead of one big model, using 10 small models, and if 8 out of 10 agrees, then we say, okay.
I think Justina will be able to answer this better, but yeah, maybe if you want to answer.
Yeah, I could come on a little bit on this. So that is more like majority vote, or you use ensemble methods try to help you to judge the alignment of data result. But the question is, it's gonna be cheaper than just use one model. Yeah.
As I was mentioning, the total cost of ownership when you're hosting even small models is very high. You need the infrastructure. Many of the small models are not cloud hosted either, right? And once again, there's always this question too, right? Like, is 10 crappy models going to be any better at saying, like, what is a council of fools gonna do? Right? Does that answer your question?
Yeah. Okay. Any more questions? So,
okay.
Thank you, Gopi, again for a nice talk.
Thank you.